Hello. First, I would like to thank you for accepting my paper for publication in your journal. My paper is entitled X-chart Analysis of Regular and Irregular LDPC Convolutional Codes on the AWGN channel, and it's in the field of channel coding and theory. The main parts of our paper are divided into introduction about the main subject, the concept of LDPC convolutional codes, and the exit chart generation, which is the principal part of our paper. Then simulation results and conclusion about the findings. In our days, the need for digital telecommunications that allow information to be transmitted from a source to destination through a communication channel by applying encoding and decoding is growing for cheaper, faster, and more reliable communication storage systems. For this reason that we always search to achieve certain major advances with a good compromise between performance and complexity. And we have chosen to work on LDPC convolutional codes because they have given performance better than LDPC codes with flexible code length, simple encoding, and more excellent error correction. Now we move to explain the LDPC convolutional codes principles, which are based on the parity-check matrix, which is divided into two parts, lower and upper, as presented in these figures, and more explained in the paper. We then copy and paste H upper under H lower for a specified number of periods as shown in this figure. From the parity-check matrix of such LDPC convolutional codes, we can obtain the Tanner graph as shown here, and which help us to know the cycles and the girth of the code. Because our paper is about the exit chart of both regular and irregular LDPC convolutional codes, we have proceeded with the exit chart of regular and irregular codes that have been developed from those of LDPC codes, and we have summarized the mathematical results in these two tables. This is the first table for regular codes, and this is the second one for the irregular case. The previous obtained results in the tables have been used for simulated first LDPC codes, where we can notice that the gap in the second figure is more open for irregular codes than the first one, as shown here. Also, for LDPC convolutional codes, the convergence in a regular case is more faster than in the regular one for both periods T1 and T3, while for a higher number of periods it is more performant, as we can see in this figure. When simulating the same LDPC convolutional codes in terms of the bit error rate, it has been shown that irregular codes give better performance with higher number of periods and iterations, as presented in this figure. As a conclusion, we can say that the influence of higher number of periods for LDPC convolutional codes have shown a faster iterative decoding convergence for both regular and irregular codes. Then, the irregular LDPC and LDPC convolutional codes have really given better performance than regular ones, and it has also been proved that LDPC convolutional codes show faster convergence than LDPC codes, as shown in the previous results. In addition to the bit error rate performance that reflect very closely to the analyzed results using the XY chart and that have also shown the performance of irregular codes and the LDPC convolutional codes that are more performant than the classical LDPC codes using both the XY chart tool and the bit error rate performance. Thank you.